I wanted y'all to experience this joy as well. So it is my pleasure, truly, to introduce our speaker today, Dr. Christopher Haak. Chris is many things, but today he is coming to us as a marine ecologist. He works at Monmouth University. Did I say it right?
Monmouth. Yeah.
Monmouth. All right. So he earned his PhD from UMass Amherst, where his doctoral work focused on biological and physical factors that structure fish assemblages in shallow nearshore habitats in the Bahamas and Puerto Rico. So currently he works with the Mid-Atlantic and New England Fisheries Management Councils, and he's developing like a model-based framework for identifying essential fish habitat on the U.S. Northeast Shelf. You should know among his many talents, Chris is also a creator at heart. So he graduated from NYU Film School and worked for 15 years in motion graphics and visual effects. So if you are a film buff and you have seen the film Hysterical Blindness on HBO around like 2002 timeframe, our esteemed speaker won an Emmy for his main title design work, which I think was so cool. It evolved into like an art form in the industry. So anyway, eventually the ocean beckoned him, and first a mere whisper and then an involuntary pull, and he left his career of sitting in front of a computer to pursue his passion for science. So in the cosmic twist of irony, it was ultimately the computer that had the last laugh. But I have it on good authority that he still finds time to get out on the open sea when he can. Anyways, my first conversation with Chris, I could hardly stay seated. I was just so excited to hear about this work at the intersection of ocean optics and fisheries science. So today's seminar is but a piece of his efforts to kind of understand and predict ways that different species and assemblages are going to, responding to a changing world. So, Chris, thanks a bunch for coming to speak with us today, and I'll leave it in your hands.
Thanks for having me, and thanks for that concise introduction, Ryan. I'm sure now everyone's going to be way too excited for, you couldn't. Anyway, yes. So thanks for coming to listen to me. I'm sorry to have pulled you out of your breakout groups. I hear you are hacking away quite productively. But so I am going to talk a little bit about the fish stuff I'm doing. I'm really interested in trying to take optics and bring it into fish habitat work more than it currently is, and physics in general. I think ecologists don't think enough about physics, and so I'm trying to carve myself out a little niche there. I want to thank some of the people who've worked on this with me, Andre Horodisky at NOAA and Zhongping Li, as well as actually Ryan's name should be on here at this point. I've meant to update this talk and I didn't have a chance to, but Ryan has been invaluable in helping to get this work rolling. So with that, I'm going to start. How do I hide my little pictures here? I'm going to move them.
I don't see anything but your full screen.
Dun, dun, dun. Sorry, now I lost it. What have I done? What have I done?
Feel free to exit and restart. This is a chill group, man. So do what you got to do.
No, I just had it, but now I've lost my slides, and now I'm just looking at you. You've taken my full screen, Ryan. Window. What do you do to make like your little windows pop up so you can select one? Ah, wait.
It's a little confusing from the speaker behavior. You won't see what we see. We saw your full slides there.
Do you still see my full slides?
Yes, but we see it like a PowerPoint. If you can go back into the mode of like slideshow.
Yeah.
Yeah.
Did that work?
Yeah. Now we see your slides.
All right, sweet. So yeah, I'm going to start talking about sensory ecology and how that plays a role in species distributions, because that's kind of been a motivating factor in thinking about this optic stuff. And we tend to think of species distributions as this thing that just the, species are here, but really, the distributions of animals emerge through the actions and decisions of individuals, um, collectively, and so those decisions and the behavioral responses that come about as a result of them are informed by information that animals acquire about their environment through their perceptual systems. They have to be able to see to find a mate, or to smell to find a reef to settle on if they're a juvenile fish, or so sensory ecology is a fundamental part of of how animal distributions are formed. And it's been likened to a transfer function that links physical stimuli to ecological outcomes via behavioral responses. And for that reason, I mean, sensory systems truly are a key part of mediating species environment relationships. And I think that's overlooked a lot in the world of species distribution modeling. So marine SDMs, as you guys probably know, are a way of relating species distributions to environmental variables. And in that sense, they're sort of trying to reverse engineer these transfer functions to infer what a species environmental niche is. And they're increasingly used for extrapolating into the future. But they really have given generally quite limited consideration to sensory systems and sensory constraints that animals face. And to the proximal drivers of distributions, as opposed to they often rely on proxy variables because they're more convenient and easier to sort of measure. And among those is depth. Water depth is obviously, people commonly describe an animal's habitat in terms of a range of depths, or but in reality, animals, there's not a lot of evidence that fish can sense depth. The only physical variable that truly varies one-to-one with depth is hydrostatic pressure. And while there's evidence that fish can sense relative changes in pressure, there's not a lot of evidence to say they can detect absolute differences in hydrostatic pressure and the ecological implications of hydrostatic pressure, and what do they really mean? If a fish goes down 10 meters, what does it mean for its ability to survive? And most, with the exception of extreme depths, doesn't have clear implications in terms of pressure. And the reason that depth is probably such a strong predictor variable and its explanatory power comes from the fact that it's correlated due to physics with pretty much every environmental variable out there. Temperature variability, wave energy, productivity, you name it. All these things co-vary with depth. And so when people throw depth as a predictor variable into their model, it's suddenly explaining a whole bunch of things. And so if you look at this plot on the right, so this is 14,000 or so observations across the shelf of several variables and how they correlate with water depth. And, over the long term, over say, this was, 14 or 15 years of data. And you can see, there's some pretty strong correlations. But when you look at the actual data points, there's clearly a huge amount of spread and variability. And so while depth is a static variable, it does not change outside of, long-term shifts in sediments, or maybe, tidal fluctuations that are more or less not, at least off the shelf, not important. Depth is a static variable, but all these correlates, or most of them, are highly dynamic, right? They can vary daily, seasonally. Wave energy varies depending on wind, and tidal currents vary with tides, and these are all there's a lot of variability around those relationships with depth. And so relying on a static variable to represent all these other highly dynamic variables introduces uncertainty into models. So whenever it's possible, finding the true proximal drivers and quantifying them and using them in an SDM is preferable. It'll give you more precise estimates of what's going on, and just a lot less of an issue with things like correlated variables that can, again, they when you have a bunch of correlated variables, your models become much more uncertain. So depth, among the correlates of depth, light is probably, certainly among the most fundamental. As you go down, it gets darker, but that the change in light with depth is also wavelength specific, and it's also a function, as you guys all know, of not just the water itself, but of these suspended and dissolved substances, plankton, CDOM, sediments, all kinds of things. So because those things these things can vary over space and time. At the mouth of a river on an incoming tide, you can have one type of water, and on the outgoing tide, you can have a very different type of water. You can, for a given depth, you can have fundamentally different optical conditions. So, for example, here are two sites, one at Sandy Hook, New Jersey, and one out on the Vineyard. They're both 16 meters of water, and these are estimates of what the subsurface light environment is at the seabed there. And one, you have, roughly an order of magnitude difference in light reaching the seabed in PAR, and pretty fundamentally different colors going from a green out of the Vineyard to a much more yellowish tone hue in New Jersey. So, fish live in very optically complex and very highly variable habitats. People have suggested that shallow coastal estuarine water is among the most photodynamic habitats on Earth. And yet fish still need to be able to see, they need to function. Obviously, its vision is critical for all kinds of basic ecological activities. So how do they manage to kind of survive in these and adapt to these demanding environments? So it turns out that physiologists have been doing all kinds of really cool stuff with this already for ages. They use electroretinography, which is basically you connect some wires to back of a fish's eye and shine some lights into it, and you can control the intensity and color of the light, and you measure the signal that's produced on the other side. And you can measure both the overall sort of luminous intensity of the response sensitivity to just overall light. You can measure the sensitivity to different spectra, and you can quantify this other cool thing called flicker fusion frequency, which is kind of like a shutter speed of an eye. So if you're an animal that needs to gather a lot of light, if you're familiar with photography, if you're shooting in a dark place, you leave the shutter open for a long time to capture as much light as you can. And fish eyes do something quite similar, and they have an integration time, and it's a period over which they collect light to integrate an image. And so things that need to see fast moving objects have shorter flicker fusion frequency, and that's something they trade off for the ability to capture. There's less light capture. So people have done all kinds of really cool work looking at dozens and dozens of species, and have found that there are some pretty clear trends in terms of animals' habitat associations and adaptations in fish visual systems. So the two primary sort of adaptations that you see are adaptations in absolute or luminous sensitivity, so just overall light gathering ability, and in chromatic sensitivity, the ability of, or the range of wavelengths that you're sensitive to. And again, you have these trade-offs that also come into play between sort of dynamic range and sensitivity and the ability and resolution. And it's really interesting stuff. And so again, yeah, so they're pretty clear sort of species that inhabit shallow water versus deeper water, or coastal waters versus pelagic waters have tended to evolve similar systems. So things that live deep tend to have higher sensitivity at the cost of lower temporal resolution, and they tend to be shifted more towards the blue spectrum, whereas fish that occupy surface waters tend to have a broader spectral response, and lower sensitivity, but the ability to see things faster. So it's pretty cool stuff. So how do we kind of go about trying to quantify the environment, the light environment that these animals are experiencing, right? So satellites obviously are making surface observations, but if we are willing to make some assumptions about the water column, which sometimes are fair and other times may not be, but just to get a sort of ballpark view of what's going on down there, we can take satellite data. In this case, we're using MODIS information and deriving IOPs, and essentially take the absorption and backscattering information and use that to propagate a given surface spectrum down through the water column, to estimate the spectrum that's reaching the seabed. This is a really cool paper that Zhangping Li published a while ago, and he helped me to sort of figure out how to do all this. And secondarily, so that sort of represents if you're linking it to fish land, this would be your spectral sensitivity. And then on the other hand, you have the overall sort of luminous sensitivity side of things, which we can also estimate just as the intensity of downwelling light across the whole visible spectrum, or PAR. And similarly, we use IOPs that are estimated from MODIS to get backscattering and absorption, and to propagate light, again, PAR down to the seabed. So we kind of estimate, we end up with these two variables, one representing the overall intensity of light at depth, and one representing the, oh, did I mention that this needs, so sorry, I skipped something, I'm backing up. So obviously when you estimate a light spectrum is many values, depending on what resolution you want to break the visible spectrum up into. We're breaking it into, I think, 10 nanometer bins. So that's a lot of values. So how do you take that kind of spectrum and represent it in a single value? Because I don't want to be feeding my species distribution model a vector of 30 wavelengths. So there are two ways that Zhangping proposed using hue angle, which is sort of a more anthropocentric way of thinking about color. There's also AVW, apparent visible wavelength, which is Ryan's baby, but kind of does the same thing, but in maybe a more physically interpretable way. But both are essentially ways of taking a given spectrum and collapsing it down to a single value that sort of represents that spectrum. So having your hue angle or AVW on one axis representing the color of light, and having your PAR value representing the intensity of light on the other, you can kind of describe the conditions that an animal is, experiencing at a given point in space and time, based on these two values. And I kind of termed it the optical niche. It's sort of so this is the combination of light and spectrum that a given animal is occupying. And also I should mention, these are not the estimates that I'm using for the species distribution model are not instantaneous values. There are 30-day averages, given that satellite coverage is often sparse in these places. So it's not like we're saying this is what a fish experienced at this very exact moment in time, but it's a sort of a good approximation of what it's likely to experience in the location that it is. So taking these and like taking, how do they look when we look at them on a map? So here is hue angle representing the sort of chromaticity side of things. And you can see it's also quite distinct between the spring and the fall seasons. This is here some of that temporal variability we're talking about. You can see in the spring, there's a lot more green water, probably related to higher productivity. And in the fall, you start to see, especially down near the Gulf Stream and along the edge of the shelf, more blue water. And looking at intensity as well, you can see some seasonal discrepancies. There's, again, the spring, it's darker in general along the edge of the shelf. In the fall, more light is reaching the bottom there. But it's interesting. On George's Bank, it looks a little bit inverted there. But anyway, so these are temporally variable things as well. It's quite interesting. So then I take these. How do we kind of relate these things to fish, right? So we have bottom trawl surveys, the federal bottom trawl survey, as well as some state level and regional surveys. I collected this data. This is about 15 years of it. Cropped it to 100 meters of depth just to try and stay in the photic zone for early testing. And picked 40 species in the survey that all had over 1,000 occurrences, and fit a model. So, and before going any more into the modeling, we're still in the process of validating. So how well do these optical models recover values, say par at the seabed or hue angle? So Ryan and I have been collecting profiles, both hyperspectral profiles and just par profiles, to look at how these models perform in terms of predicting what's happening underwater based on, obviously, surface data. And for the most part, they do a pretty reasonable job. They're not perfect, but they perform reasonably well. So sorry, back to the species distribution modeling side of things. So to take a look at this, I fit joint SDMs. So it's basically a hierarchical model that when you're fitting the species, you kind of can share information across them to achieve a better fit is the goal. I'm not going to get into the details of that. It's probably don't even need to know that. But so basically comparing two models. One, so we had a set of common predictors that were in every model. These included temperature, salinity, several other hydrodynamic variables, and some benthic sort of terrain and sediment related variables. And then fit the model that, given those common predictors, fit a model that included depth, and then a model that included the optical niche to compare how they perform. So, and held out a 10% of the data set for testing. So just looking at prediction, the optical model did a lot better in terms of AIC, and in terms of out of sample prediction for 38 of the 40 species, it performed better. And the only declines that were clearly there were in 3 species that were all very deep. They're deep water taxa, and given that we're looking at a max depth of 100 meters, we're kind of truncating their habitats. So we're not doing a very good job of representing their niche as it is with the model that we're working in. So in general, the lower AIC indicates that despite being a bit more complex, because we have this tensor of 2 variables instead of a single variable, it's still performing considerably better. And just looking at the significance of predictor variables, optics was, in addition to temperature, was they were the only 2 variables that were significant across all species. And it explained the second or third most amount of variance across all the predictors. So that's pretty cool stuff. I mean, it seems like it works, right? Well, so looking at it from the ecological side, it gets more kind of interesting and fun. So we picked some example species. So you can see on the right, the sort of response surface there that's in color represents the sort of estimated optical niche for these two species. These are smooth and spiny dogfish. So the yellow in that gradient represents the sort of peak of where the peak optical conditions that they're occurring in. And again, so on the vertical axis is absolute intensity, or the PAR side of things, and on the horizontal axis is the spectral side of things, the hue angle or AVW. And so Kalinowski et al. Did ERGs, electroretinography, on both of these species, and that's what you can see on the left. So we're only considering daylight sort of situations here, so you would be looking at the white dotted profiles that they have there, and so those represent their spectral sensitivities. And on the top is an estimate of their that top little bar reflects their luminous sensitivity. So basically the findings from their study was that smooth dogfish had a higher luminous sensitivity than spiny dogfish. And they found that the spinies had a spectral response that was shifted towards the blue more so than, or sorry, the smooth dogs have a blue shifted spectral response, spectral sensitivity curve. And just looking at our estimated niches, both of those sort of differences play out pretty clearly. The smooth dogfish are occupying darker habitats. They're sort of that black spot dot marking the peak of their sort of distribution is down low, considerably lower in the light intensity spectrum, and they're shifted towards the blue wavelengths relative to spiny. So the fact that these kind of sort of relatively subtle ecological differences that have been documented in the animals become apparent in the estimated optical niches is pretty neat. Just another quick sort of example. So summer flounder, scup, and black sea bass are all managed under a common fishery management plan because they show very high overlap in habitat use, and when there are fish, they're often collected together. And so just looking at their estimated optical niches, you see that they're all very, very similar in terms of being kind of relatively wide dynamic range, pretty high sensitivity, but also suggests they occur in shallower water as well, or I should say brighter water as well. And they're all kind of share a similar peak around in the greens for their spectral sensitivities. So where is all this going? And yeah, so it looks like the optical habitat, the optical niche concept kind of works. It definitely provides a more interpretable sort of way of thinking about things, the depth. It allows you to bring more covariates into the model. I didn't do that in this case because I wanted to keep the comparison fair, but because there's much less collinearity among the predictor variables when you get rid of depth, you can bring in other things that are also, if you're trying to manage collinearity in your model, addressing these proximal predictors really helps. And thinking about this, what gets interesting is if the optical niche is a real thing and it's important to and it makes sense that animals need to be able to see to function. A lot of people are talking about how warming is pushing animals deeper and or farther north, and that means also to places with less light. And what does that mean? Thinking about how these sort of distribution shifts are going to affect the ability of animals to function, and their match mismatch between their visual systems and the environment, the optical environments they're occupying, is something kind of interesting and cool to think about. There's still lots of caveats, obviously. So we are simplifying things by assuming that the water column is heterogeneous, or sorry, is homogeneous, when it is certainly in many cases not. Things like deep chlorophyll maxima occur, and trying to find ways to deal with that is important. This model at present is omitting depths greater than 100 meters, and like, as I sort of discovered in the process, that does mean you get biased estimates for animals, especially animals that are using deeper water, that you're sort of truncating their niches. So future work will look at a broader depth range. Again, let's see. Right now I'm just pooling adults and juveniles, but they both often have pretty distinct habitat niches, and there's work showing that their visual systems also develop over time. So looking at looking at some ontogenetic stages is probably worth doing. And obviously, these optical niche estimates are really only as good as the data that we have to fit them to. So trying to bring in more surveys that represent a broader spectrum of environmental conditions, estuarine conditions like Long Island Sound or Chesapeake Bay, would really help to also kind of make this work function better, I think. So yeah, ongoing things, right? Expand the fish survey to include other regions, keep working on validating the light attenuation models, and adapt those models to incorporate water column heterogeneity. We could probably try to use, obviously there's not a lot of data on vertical water column structure that's, in any form of spatial or temporal resolution that would be useful in a broad scale SDM. But some biogeochemical models, like ocean models that include a biogeochemical component, could provide some information. You could pull chlorophyll profiles or something that you could then use to modify the attenuation scheme. It's also worth expanding the spectrum, if we can, to include the ultraviolet. Right now, that's not in there, but some fish species do utilize UV or can see in the UV, and something worth considering. And linked to that is trying to move this whole thing from using multispectral data to hyperspectral data. And PACE is obviously an ideal test bed for that. One of the challenges with that is that at the moment, as far to my limited knowledge, the attenuation, the KDs that are produced for PACE are produced using a standard sort of QAA approach that only pays attention to a certain range, a certain set of wavelengths, not the entire spectrum. So being able to for ways to really exploit the hyperspectral nature of PACE is high on the list for this work. And also trying to look at not, so, I mentioned that the data is only as good as the survey data that we're looking at. Those surveys, the trawl surveys, are sparse in space and time and few and far between. Having something more like individual movement data, animal movement data, that's telemetry data that we could use to kind of test some of these same methods, but with individual animals and higher spatiotemporal resolutions that also include changes in depth use or something, would be a really, really fun way of expanding this. Anyway, I have talked too much. I want to thank various people here and Ryan and Eli for inviting me, and I want to thank you for tolerating me and listening to my chat. Any questions?
Sweet. Thanks, Chris.
Sure.
Yeah, everybody has